Thank you for attending this course. I would like to start today with a discussion of the notion of the support, respectively the spectrum of the distributions. So let us recall that our setting is we have been starting with the idea of convolution of bounded measures. This was the starting point. We were starting with bounded functions which decay at infinity, which is a very nice and decent space, actually a pointwise Banach algebra. Then we were identifying the space of all Bibel's system, all operators acting on this nice space and commuting with translations, and this is very important. And we have found that you can characterize them as moving averages. We say convolution with bounded measures, and that of course the composition has to be somehow reflected, and that's how we define the composition of measures by convolution. Now inside of the bounded measures we find the descent measures, which are introduced by continuous functions with compact support. They are not a closed subspace, but we can close it up. So we take the measures which are approximated by nice convolution operators in the norm, the operator norm of the convolution operators, or in the Banach space, dual space norm of bounded measures. And we call this L1. If you're trained in measure theory, then you will recognize that this is one of the completions of the space of bounded continuous function with compact support, endowed with the L1 norm, which you can define with the Riemannian sum. And so you have just a concrete model now inside of the bounded measures. Then we went on to obtain a space which is Fourier invariant and still allowing this embedding of identification of certain nice function and dual elements, which are the distributions. So instead of discussing at length the dual space of L1, which normally would be L infinity, I have done some comments on this earlier, the essentially bounded measurable functions, actually with identification of two such functions, if they generate the same functional, which is the same as assuming that they're equal almost everywhere. So this would be L infinity, the dual space. Now, in the book of H.Reiter, and I wanted to mention this at the beginning, you find the notion of the spectrum of an L infinity function. And so he would go on and say, well, you have to do it in an indirect way. So we are in the middle of this page now. Sorry, one more. So you define the annihilator space or annihilator ideal. What does it mean? You're saying I'm taking all the L1 function, which, and you see here, the star is the flipped conjugate, and that's the adjoint action. So which by the adjoint action, but you can say which essentially up to this flip operator are convolving the given function phi in the dual of L1 to 0. So even if we take an abstract viewpoint, we could say phi is a functional applied to a test function can be defined pointwise, take the functional applied to the flipped shifted version of f, and do this for all translates of the function f. So that's not surprising. We can do it the same. So this is clearly a subspace of L1, but it's a closed subspace and it's even an ideal. If you come up with another function, let's say g in L1, and you convolve f with g, then you will find out that 0 convolved with g is also 0, or g star. So this is a closed ideal. And now the definition of the spectrum, I would say the relevant frequency content in a very, very indirect way is obtained by saying, well, we have to see where this ideal is not having any information. So we define the co-spectrum. We're saying, well, if you take this here, for example, you might convolve with the sinc function. That would mean you apply the Fourier transform to this convolution relation, you get 0. well, that means that the phi hat would be 0 on the interval. So you're saying, what are the points, frequencies, such that the Fourier transform has to be 0 because of the action of this. So kind of the spirit of this is here, if we go to the Fourier transform side, if f is non-zero, or if phi hat is non-zero, phi hat multiplied with something can be 0 only if that something has a 0 there. So that's the indirect way of defining a co-spectrum. And that's actually a typo here. The spectrum is defined as the complement of the co-spectrum of the associated ideal. Okay, so this is a very indirect definition. And when I was taking this course, I was not realizing that it has to do anything with pure frequencies or so. So this terminology didn't appear. However, it was a way to describe that you are saying, well, if you want to find those frequencies, then you can identify them, and here you have the pure frequencies as those frequencies which can be obtained from the given distribution. It was just the phi here before, by taking the closure of the convolutions with nice functions. Or, as you find it in the early literature, you're taking the closed linear span of the translates. But we know already that any convolution with a nice function can be approximated also by a finite sum of translations. So if you replace the hn by deep psi hn, the discrete version, you get a finite sum of translations. But on the other hand, if you give me a finite sum of translations, you can take a corresponding finite approximation to the identity and smooth it out. And so it's a discrete measure approximated by a collection of Dirac functions. And then you get this. So this is really the same. So that's actually one of the main goals that we are having for the first unit. So we're in section 22. And so I will try to show this to you and go through the details. Now, in the preparation of this, or as a part of the material for today, I will need something that I actually also took from the book of H.Reiter, which is a fact concerning a closed ideal. It's the ideal of all the functions in L1 having a Fourier transform 0 at 0. Of course, it's just an example. You could take any other point and get the similar results, but it's more convenient to take this because it's the prototypical thing. So essentially, what I want to explain to you, that it's one of those ideals, and that it is a maximal ideal, and what kind of consequences this has. So the first thing is, of course, if you multiply two functions in the sense of convolution in this space, you get a function, an element in L1, which has the same property just by the convolution theorem. Actually, any L1 function can be convolved with this, and you would look at G convolved with such an F. The Fourier transform would be G hat with F hat at 0, which is 0 of any way. Well, it's even a closed ideal in the bounded measures, but that's what we don't need. The statement that is interesting is that we are saying that this is a Banach algebra of its own right, which has bounded approximate units. And this will be used in a moment to create on the Fourier transform side an approximation by multiplying with such bandpass filters. So the terminology of engineers would be, if you multiply the Fourier transform and you let through only frequencies, let's say between 5 and 120, and you do it in a smooth way, which of course means that you're doing by convolution with a localized filter, then this is a bandpass filter, and such bandpass filter can be produced with a norm which is at most 2, or which is limited by 2. Now, the proof is not very fancy in a way. It just says, well, of course, first we start with an approximate unit. So we take an L1 function with integral 1, and we know the integral is just Fourier transform at 0. And then we compress it to get a Dirac sequence. All the elements of the Dirac sequences have L1 norm 1. And then we also know that the ST row of G, so I have again to do a correction here, convolved with F minus F will go to 0. This is fine, but of course ST row of G is always a function with integral 1. So this condition also for the dilated versions, this is dilated version of this, the Fourier transform, they all have 1, and therefore this is not belonging to the ideal. Now the trick is, and I will move in between for a moment to GeoGebra. So I show you how I describe the situation in GeoGebra. So maybe I eliminate, but this was like a 5-minute experiment. At first I take the Gauss function and I really just type in g of x is e to the minus pi x squared. You can ask GeoGebra to do the integral and you will find it. That's the normalized version. It has absolute value 1 at the peak. It is invariant on the Fourier transform, but one has to mention that the L2 norm is not equal to 1, but it's you can compute it easily. Now I'm doing dilations of this function here. So the dilate is now a Dirac sequence. So this is producing a Dirac sequence. Maybe I move it a little bit up and down. So in this way, that's what we have seen here so far. We have a function which is fairly compressed by making a row small enough. Okay, it's difficult. Okay, but we have seen that it's not in the ideal. Its Fourier transform is, of course, another Gauss function. So what we do is we subtract another Gauss function, which, however, is now a very much stretched, so a very flat guy here. And the trick is to take the difference of those two. So if I remove this here, so you see we create from this Dirac plus something which is very flat. And the point is to prove, now you can play around and make it a little bit more stretched, and this a little bit more peakier. So these functions, but you can start with anything. You can take any function here, and we will do it particularly with something like the de la Vallée-Poisson kernel, which is the Fourier transform of the trapezoidal function that will give us these bandpass filters. So this is the idea, and so I'm going back to the plot. Take a new one. Yeah, so we are at equation 434, the current enumeration. So we say, well, if you give me any f which has integral 0, so one of the things from the ideal, then we can find out that if you do a convolution with the second guy, this flat guy, so practically it means you take a big average. Well, but if you take a very big average and you know that your function has integral 0, it's clear that pointwise this average will be small. But will it be also small in the L1 norm? And then you have a very simple one-line computation, which I will explain to you. We know that the ST row operator has two very good properties. First of all, it's an automorphism, which simply means that you can either apply it to a convolution product or to the individual factors. So what I want to do here is I want to read this as a, well, stretched in the decompression sense, a stretched version of something. Now, the first factor is already coming with this symbol, but the second factor, I take the inverse of the stretching operator. So if you kind of multiply out, you're seeing that you should take the automorphism property, so you have to take the f, it's compressed and then decompressed, so you get your f back, convolved with, and then you decompress the g. Okay, that's fine. But st for any parameter is isometric, so you can leave out this term and you're getting g convolved with stf. But now you're seeing that it's a convolution product of a compressed version, but you see the roles of g and f have been changed. So we have done this already. The g convolved with something that I compress, it converges to the multiple of g, but the factor is just the Fourier transform of f, the f hat of 0, so of the compressed guy. But we know this is 0, so I can insert it without error. So of course, because this is 0, yeah, we can make this arbitrarily small. So okay, by decompressing our window g and by taking a sum of a compressed version, that should be the g, and decompressed, we're getting a function which is called f rho, which was the guy that I was showing you in the GeoGebra argument for two Gaussians, but you can take anything. One used for the compression, for the Dirac measure, and one for the taking the mean values, the huge mean values. And now each of them has norm 1, so the difference will be actually very close to norm 1. It will not cancel out very much. And so it's inside this. And of course, if you combine it, you are saying I'm applying the st rho of with smaller rho, and then the 1 over rho. This f rho will have exactly the same action as the good guy, because the other one is having a minor contribution. I was putting 2 epsilon over 2 here so that everything is fine. So as I was already indicating, I will use this to come up with a function which has a trapezoidal shape, so it's like this. And that trapezoid, of course, here I didn't take it too big, should be dilated. You remember st rho on the time side gives you d rho on the frequency side. Compression gives you Dirac sequences. On the Fourier transform, it's stretching the value at 0 to infinity. So it's a big trapezoidal function. But you also subtract a tiny one because this is the compressed version. This is the minor guy. And because this was 0, you can flatten out and you can approximate now any element in I0, in this maximal ideal, by other functions which have a finite, compactly supported Fourier transform, which means you approximate it by band-limited functions, plus you get an extra freedom, a very tiny but positive interval of positive length. Of course, the same thing can be done in a multidimensional situation. You just take the same proof and draw different pictures. So the statement is summarized in the following lemma. If you give me any such function in this ideal, and I call it a maximal ideal, in an epsilon, I find an approximation by something where the Fourier transform of this approximation is compact and disjoint from 0. So there's a kind of security distance. Now, I have a rather lengthy explanation of spectrum and dual spectrum and support of distributions in mind for today. So let me continue with this in great detail. So what is the idea? Well, we want to understand what it means that the Dirac delta is 0 everywhere except at the point 0. And I keep pointing out the distribution or such a functional doesn't have values. Even if you would think of L infinity as a dual of L1 in the measure theoretic sense, you would always allow to change points on a countable set, because countable sets are sets of measure 0. That's not true in the converse, but so whenever you have a function in L1 or L infinity or L2, it's an equivalence classes. You could throw in countably many points, for example, a countable set which is dense in the interval 0, 1, and suddenly the support in the naive sense of taking all the values where the function is non-zero and closing it up would be increased by that interval. So it's not meaningful in the LP theory to talk about the support as you do for ordinary functions. So for ordinary functions, we have this standard definition, take the values where the function is non-zero and take the closure. So what one has to do is to do it in indirect way. In the original lecture notes, I'm discussing at length different conditions, but I think for now it's better to take the most efficient description, maybe not the most intuitive one, and tell you about the rest. So we talk about where is a distribution zero, and we are not talking it's zero at a point, but in some region, in some area, or let's say better, near some point. The distribution is acting trivially around the point t if we can find a localizer, a function which is continuous. Yeah, actually, we should take it from S0. Yeah, so in the case of S0, with arbitrary small support. No, sorry. It's trivial if you can find a function which is 1 at the place, but still the product of sigma times k, and remember sigma times k at f is sigma of k of f is 0. So it means, yeah, here you have it. If sigma k of f is 0 for all f in C0, respectively S0. So we have two definitions. One definition is if you give me a bounded measure, a functional, so that would be mu. What is the support of a bounded measure? Then you would refer to C0 elements, or you give me a mild distribution, an element of S0 prime, and you would have this. Now we have seen already that S0 is dense, or the elements of S0 with compact support are dense in C0, and the compact elements here in the uniform sense. So if you look at the measure as if it was only a measure or as an element of S0 prime, mild distribution, this would not change the notion, so that I should maybe add this also here. And now, yeah, there's again something I have to correct. A point T is a point of trivial action, and of course I should say it's not in the support, does not belong to the support, and the support will be the complement of the area of trivial action. So kind of, let's say a point, we have trivial action if and only if you find that all functions which are supported near this point are getting a 0. So kind of, maybe I should rephrase it in words. If you're asking me, is T a point which has trivial action, then I would say, well, I think yes, because I find a small interval around this point such that all the functions f, well, in the Fourier algebra in the 0 or here in CC, which are supported here are showing trivial response to it. So let's take, for example, the Dirac at 0. We have trivial action for any non-zero. Well, you would say, you give me some small value x near 0. And I would say, okay, the distance from 0 to x, so the absolute value of x is a positive number. Let's take a small interval around x, which does not contain 0. And you look now at all the test functions which are living in that small interval. Clearly, their value at 0 is 0. That means our delta 0 of such functions would be 0. So kind of, we have a trivial action of the Dirac delta defined as the pointwise evaluation at 0 for any x which is different from 0. And that's the mathematically correct way of describing the support. Now, we can show that this concept is equivalent, but I would like to skip this here. Essentially, it means that you use the Wiener inversion theorem in the case of S0 to define that these two definitions or characterizations are equivalent. So the more intuitive one is you're trying to use your function, but only apply to test functions which are very localized near the point. If your localizing ball or neighborhood is small enough, you should see no action. And the other one is my formal definition. Some set point is in the support of f. Yeah, here is the formal definition, the blue one, if it's in the complement of the trivial action. Now, an important statement, and actually the reason why you take a closure in the classical definition is the fact that this is always, this definition implies that you get a closed set. Now you learn that a closed set is exactly a set which contains all the limiting points or where the complement is an open set. So what we have to show is just that you have an open set. Now the fact that you have an open set, maybe I don't go through this, you can look at this yourself. With the second characterization is quite easy, because assume you're sitting at a point, maybe I'm going back to this here, I'm not sure, yeah. You have this situation. You have an epsilon ball around your point of trivial action, and then you take any point in the interior. So maybe you have a ball of radius epsilon around t, which is completely containing test functions which have no action. Now, if you give me, or if I tell you, look at all the points which are in an epsilon 1/2 neighborhood of the center of point t, then you can still make another ball around that new point y, which also has a radius epsilon 1/2, and you're still inside of the original ball of radius epsilon. So kind of the story is if you have a big ball, all the small elements in the inner circle can be surrounded by a small ball and it's still in the area of trivial action, and therefore this is an open set. Okay, now yeah, of course we have to describe the consistency of this situation. That means if you take the classical definition, so for a continuous function with compact support, you're taking the closure, this bar means take the closure of the set of all t such that k of t is different from 0. And then you will find that this can be viewed as a distribution, so you have a sigma k, and the distributional support is the same. I think it's quite clear how to do it. Think of the classical support because of this function. This is a closed, I mean, by definition, it's a closure, it's a compact set. And if you have a point which does not belong to the compact set, then there exists some epsilon ball around it, such that on the whole epsilon ball, k is constant 0. Now, if you take any, okay, now you should not take k, but that should be corrected by f. If you take any f, so this f should be here, which is supported, okay. Yeah, I think I should leave out this text, but if I take any function f which is living in such a small interval around t where the k is trivial, and then you let it act, which means you integrate your f, this should be f, against k, then of course you get the product of two functions which are 0. So you see here, my f is the k0, and therefore the integral is 0. On the other hand, assume that, yeah, I mean, probably this was done long ago. If you take now complementary, you take a point which belongs to the support, it means that you have very nearby, in any neighborhood of this, you have values where you have non-zero values, and therefore you can find some function f which is acting in a non-trivial way. So I have to just expand this and redo it, sorry. Now, the main point was to say, well, whereas the L-infinity case has to be done extremely indirectly and non-intuitive, we are now in a situation where we have the Fourier transform of our mild distributions. And so we just use the classical definition of a support, I mean classical in the sense of distribution theory, combined with the Fourier transform and say spectrum, well, these are all the relevant frequencies in the signal, and so we call this support of the Fourier transform. So again, sigma in S0 prime means the Fourier transform is in S0 prime, so it has a well-defined support. Now we come to the closure, let me see, to the statement, we say a pure, so this is a subset of the frequency domain. And so the classical characterization would be the following. Pure frequency, chi s, belongs to the frequency spectrum or the spectrum of sigma if and only if it's in the weak star closure of the linear span of the translate of S. So that means you're able to take get a better and better, in the sense of weak star, approximation by taking finite linear combinations of translates of your original sigma. Now, since we know that mutual approximation that I have mentioned already of linear combination of translates and convolutions, we can also say that's the same as a zero convolved with sigma can be approximately like a pure frequency. So if I have a frequency S in the spectrum in mind, essentially what we have to do is to say, well, instead of taking linear combinations of frequencies, convolve with elements S0. And we know that convolving with S0 is essentially the same as multiplying on the Fourier transform side. And multiplying on the Fourier transform side is what the engineers call filtering. So somehow these are all possible filtered versions. Now, whenever you convolve a test function with a mild distribution, you get a continuous function which is actually uniformly continuous. So what we are saying or anticipating is, well, these things should approximate a pure frequency. So imagine you have your system, convolution operated by sigma, and you feed in decent functions. What would you expect to get out here? These are things which have approximately compact support, so they are finite signals. And then let's say this is a bounded measure. So this will be a finite input response, and that will be a finite output. So in which sense can this be convergent to pure frequency? And the answer is, well, more or less in a compact open sense. So that if you give me a pure frequency, which is in the spectrum, so you expect that it is relevant for the measure. So roughly speaking, you would say it's not completely vanishing on the Fourier transform side. Then you would expect that you can filter it out by letting the input be a long-lasting plateau-like function with the pure frequency S. And the output will be something looking very much like a long part of a pure frequency, and you can do this better and better. I mean, even better local approximation and so on. So this will be the story. And I have tried to formulate it in a more mathematical way, and that's kind of the rest of the first unit now. So the formal definition is the following. I'm saying what are the, maybe I should also call them no, kind of, yeah. I do it on the time side more or less. So I'm saying the elements of the support are the elements, so kind of the relevant elements in the distribution sigma are the ones which I can get out. Now I'm doing, instead of convolution, I'm doing pointwise multiplication on my sigma. So you're asking me, what is the support of the function? And I'm saying, well, these are the can be described as the Dirac measures, which can be filtered out by multiplication with localizing functions. So here you would think of K alpha being a Dirac-like element located very near to the delta t. So this is what we want to prove. And the proposition is a technical here, and I have spent some time on trying to get a proof which is at least self-contained. I mean, I would suggest that please take this only as a proof or demonstration that it's feasible. It's not that I'm expecting that you're studying the details of this, but the fact that the spectrum is the set of all frequencies which are found inside of the signal, which can be filtered out in some very natural way out of this. And that's really the spirit of spectral analysis. This is what I hope is staying with you. But it's also a good exercise in showing you what are the tools and why are these properties of S0 and S0 prime useful. So slowly and starting from the beginning or so, we are saying, you're giving me such a mild distribution. And I would like to characterize that a point is in the support of such a distribution. And we have to do it without point values, if and only if, and now I'm describing weak star convergence. Something is near in the norm if the difference in the norm is small. Something is near in the weak star sense means you're giving me a positive epsilon and a finite set of test functions. And I'm saying this is from the first to the last functions f inside from your space. We're in the dual of S0, so we are taking elements from the space. And the claim is, I'm claiming that I can approximate by multiplying the sigma with k, so that I'm saying, then I will be able to tell you how to find a compactly supported function in the Fourier algebra, which is the same as a compactly supported function in the S0. So the compactly supported function in the Fourier algebra, they are decomposed into finitely many pieces, so clearly they are inside S0, such that my test, and the test is, well, take your function k, multiply it with sigma, and the claim is that this is close to delta t of f, but delta t of f is f of t. So for every point, you're giving me a point in the support, and I have to demonstrate how to find such a k. Now, in reality, I will show you, the proof will give you that I can even make sure that this multiplication gives me a continuous function on the Fourier transform side with a subnorm at most 2. So I'm saying, well, on the Fourier transform side, I can control sigma k will be a function with compact support. So this element will be a continuous function, and this continuous function will be bounded. So on the Fourier transform side, this will be bounded in the subnorm sense. Therefore, it will be bounded in the sense of S0 prime. So I will create a bounded family of things which are, in this sense, in the weak star sense, convergent to delta t. Okay, now I'm doing a number of restrictions or simplifications which came out during the writing of the proof. And the first thing is, whenever you ask to do this for some sigma, of course, you can rescale it. If it has norm 5, divide sigma by 5, and once you're done with the proof, you're multiplying back. So we can assume that it's normalized, and by shifting the sigma to the position 0 or the t to the position 0, we can assume without loss of generality that that the point t is 0. Otherwise, whatever you're doing with your k, you also shift the k to the same point. This is a modulation on the Fourier transform side, so nothing will change if we do this special case. Now, assume you have chosen your very small epsilon, and you have given me a big finite set to make my task very difficult. And then, of course, again, to save complicated terms, I would say we can assume that the Fourier algebra norm, which is the norm of either f hat or the inverse Fourier transform in our normalization, that's not the difference, that each of these elements has norm 1. If you are taking elements with a different norm, you just rescale everything and you've got another constant. Now, what we will need is that we would like to say, well, basically, we would like to have these elements to be band limited. So if you give me an individual or even finitely many elements in a 0, what we know is their Fourier transforms, or their inverse Fourier transform actually, are also in a 0. And therefore, maybe I'm looking at this term here, I can multiply it with a plateau function such that the difference is small. So this is maybe the crucial point. I'm, for convenience, assuming that the plateau function can be chosen to be symmetric or an even function. And what we really do is we have seen that the partial sums of the decomposition, so f hat is the sum of f hat multiplied with psi k. And so I would just take the sum of psi k from k minus 100 to plus 100, or all the psi k's which k absolute value is less than 150 or so, whatever. That is such a symmetric function. Because this is just the remainder of the summation, this will be small, but we also know that the 0 norm controls the L1 norm, and the L1 norm is flip invariant. So we will need something on the inverse Fourier transform, but we get it from approximation. So roughly speaking, I'm assuming more or less, you would say, but this is what I will take into account. We think that it's practically a collection of band-limited functions. Now, what we also need is, and now we use this lemma that I did before with this band pass signal. So this was a trapezoidal function. So the trapezoidal function is just a function where which is constant 1 on the Fourier transform side. Sorry, no, it's a function which is constant 1. Here I found it's better to just assume it's a trapezoidal function which is constant 1 on the unit ball, because I will dilate it anywhere. So you can say I take a big rectangular function, maybe supported on minus 3, 3, convolve it with a small rectangular function supported on minus 1, 1. And then I get the trapezoidal function, and I can normalize it so that it has norm 1. So there's no problem to get such a function. Now, because we're inside of a 0, we know that the Fourier transform is also in a 0, and therefore it will be in L1. Now, whatever we choose here, we know that it has a continuous translation in L1. That means, well, if your translation parameter set is not too big, so the epsilon is the epsilon that you have given me, so I can choose my tau, and once I have chosen the tau, I can find a delta such that everything is okay with epsilon over 4 to make things nice. Now, what we can do, of course, is we can dilate this function, and then we have to dilate in some sense, and then we will get that the dilated version, so kind of it's now made smaller and smaller, it will be for large rho only constant 1 for u, also less than 1 over rho. So you see from diameter 1 of the plateau, I shrink it to 1 over rho, but that's not important. I will just use that. Now, what we know is this pair tau and tau hat are Fourier transform of each other. I'm not sure, maybe I should assume that the tau has been chosen flip invariant, and that's clearly true. And so we have that if we do a compression of this tau hat, then this will be a useful thing. And in the sense that if we compress this Fourier transform by a parameter which is now dictated by two numbers. So in the first step, I didn't spell it out. You have given me some epsilon and some collection of functions. And in order to localize it, we need some plateau function. And these plateau functions have to have some finite support. So we choose a radius r, maybe a very big radius or so. Then we were looking at this trapezoidal function, and there was a delta involved, maybe a very small value delta. Now I'm saying, well, I will do the following. I will choose rho fairly big, multiplying the big number r or by the inverse of the small delta. So it's a product of two big numbers, but it's a finite number, and we fix it. Now I'm saying, if you're giving me any element from where the function p is non-zero, so inside the ball of radius r, and you compress it and you divide it by rho, then you are inside the area of delta. That means, and that's the point that we will need, if you take the Fourier transform of this very narrow compressed tau, and you compress that further on, you kind of stretch it. So you're stretching, we are compressing the tau to have a small plateau, and so we are dilating this to a flat. So this was more or less something like the second guy in our GeoGebra experiment. So we're saying, you're giving me a V, which is in the ball where the P is supported, and then I will find out that T, the translate by V of this guy here is small, Y. Now do the same trick. Now I'm doing the commutation between dilation and translation. Translation. So if I stretch a function and then a shift, I could have done the shift in a smaller amount and then do the stretching. So this is a very simple notation, and this is the ST rho applied to tau hat. But now we see that the ST rho is isometric in the L1 sense, so you are left with the T of V over rho of tau. But now the point is that for any V that we have, it's at most R, divided by a fairly big rho, this will be a tiny parameter set like in 450. Therefore, we can use the estimate here and get epsilon over 4. Okay, now I think I better continue with the proof and take the break only later. Sorry for this heavy part now. So by the definition of zero being in the support, the only thing that we can know is that we can choose functions which have smaller and smaller support. So we can take these functions to be supported in balls of radius 1 over n, such that each of those sigma multiplied with kn is non-zero. So kind of that's. Now, what does it mean? It's a compactly supported function, distribution. So if you go to the Fourier transform domain, it will be a continuous function. Yeah, maybe here I'm writing. If you give me a k, such a k, so I call it just k without the label n, you can reproduce it with a plateau function and can take, again, maybe a dilated version of the tau that I had before. Or yeah, the n is bigger than 1, so 1 over n is less than 1. So this is all supported on where my original tau was okay. Now, k is the same as k multiplied with tau. So again, this reproducing property, that means that sigma k is reproduced by multiplication with the plateau function. What does it mean on the Fourier transform side? Sigma k hat is the same as sigma k hat convolved with tau hat. But this guy is in S0, so we have a convolution product, and this just guarantees that this is meaningful. And of course, if it's non-zero, this also will be non-zero and the norm will be non-zero. So we are getting more and more concentrated functions k, and their Fourier transform after multiplication with sigma is non-trivial. Now, what we do is more or less we're rescaling each of these functions. So we're just saying, well, we would like to have a value where this function is attaining the maximum. Now, to be careful, maybe it's a function which asymptotically reaches the supremum. Therefore, we just say we can pick a value where it's near the peak value, where the value is 1, despite the fact that this is 2. So you're just taking whatever this function has, you rescale it. Maybe the maximum of the function is 1/5. You rescale it, multiply it by 10, then for sure you find a value where this is, maybe you should say the absolute value is this, but by replacing the k by another k, you get to that it's even positive and exactly 1. Now again, a simplification. We may assume that this is anywhere, but if you multiply your k with the corresponding frequency or with the negative of it, you can guarantee that this is at 0. So we are in the situation that we have sigma k is now constant 1, no, is equal to 1 at this here. So we are able to fabricate this arbitrary small function, a function with arbitrary small support, such that on the Fourier transform side, this is a continuous function and takes the value 1. So it's just by manipulating on the original k that we got, by rescaling it, by multiplying with some frequency. All these things do not change the size of the support. And of course, we don't know how big the k is, and it may be quite big, especially if you think if it's an ordinary function value and it's 0 of your original density or so. And now we're still not done, but I will try to do it in a consistent way. So the point is that I give this function a name, this sigma k. So this is the interesting guy. And I would like to demonstrate that it's not only 1, but very close to 1 on a big interval, actually, where the p is living. Okay, so I introduced just a new name because this allows me to fit everything in one line. I called it H. So that's the Fourier transform of sigma k. The normalization tells us h of 0 is 1. Now we look in this radius. So what is 1 minus h of z? Well, it's h of 0 minus h of z. But now we have to look at this reproducing property. We have yeah, maybe there's, I'm not sure. Yeah, okay, no. I have to check this, but essentially, maybe then the denomination of h is not correct, but this is kind of what we should look at is sigma k hat, and sigma k is reproduced by multiplying with this t. Yeah, okay, so no, it's true. We have sigma k is multiplied with tau without change. So that means on the Fourier transform side, we can reproduce with a multiplication with this tau. So kind of we have this here. So we write this at 0, and the same thing now. Instead of saying at 0, we say we are shifting it by set. Actually, probably we should, yeah, okay. And the convolution product, that's the other point, is that shift is done only on one factor of the convolution product. But now we're in the situation, this reproducing pointwise reproduction production gives us that h can be pulled out. This is a bounded function. And the rest is the thing that we made less than epsilon over 2. So it's this shift invariance of this broad guy. So this can be made small. So the consequence is that 1 minus h is almost 1 on a very big set. And now we are saying that we're going for the delta, and we're doing it on the Fourier transform side. So the distribution coming from constant 1. Oh, yeah, sorry, one more thing. In order to save symbols, I was introducing a G, which is the inverse Fourier transform of f. And it's any one of these finitely many f's, or it's the Fourier transform flipped. So we're saying if you take the constant 1 distribution on the localized GP, so that would be more or less f hat at p, or you compare it with the multiplication with h, then of course you are having the g, the p, and in between the 1 minus h, and now I'm rewriting it as sigma k hat. And we have seen that on this set where this is non-zero, so this is the Boloff radius R0, you're getting a deviation of epsilon over 2. This p was supposed to take values between 0 and 1, so you can neglect it. And the remaining thing is the GL1. And by definition of our normalization of the f, this was the Fourier algebra norm of f. So this is epsilon over 2. So we have seen that if we localize our Fourier transform of f hat more or less, then everything is fine. And so it's just a standard epsilon over 3 trick to say if we take the g and the deviation to the sk hat, so that's the h, then you have the epsilon over 2, which is the error that we have between these expressions. But then, of course, we have to remove from gp to g, that's the first term, and we have to move at the s sigma h from gp to g. Now, we have chosen that the h hat is at most 2. That's why I have 2 over epsilon over 6, and this is 1 over epsilon over 6. But of course, everything is made such that it adds up to epsilon or so. Now we are already almost here. So here you have the Fourier transform of constant 1, of delta, which is constant 1, applied to the inverse Fourier transform of our f, minus the sigma k Fourier transform applied to the inverse Fourier transform of g is small. And so we just have to reassemble everything. So maybe we use this formula. The definition of the inverse Fourier transform applied to a Fourier transform is, well, take the tau, the distribution, applied to the inverse Fourier transform of your argument, which is f of f, which is of course f. So we use this formula twice, both for this and this term, to come up with the sigma 1 of g is actually the delta 0 of f, because 1 and delta 0 correspond to each other. The sigma k hat is the h, so the sigma h is corresponding to the sigma k of f. So sigma h of g is the sigma of the Fourier transform of sk to the inverse Fourier transform of f, which is exactly sigma k of f. So we have exactly obtained this, which if we rewrite is f at 0. That was our interesting point of the candidate for support, and minus sk, and we get this epsilon. Okay, I'm just mentioning, so we have seen that if you give me a point in the support, so the hard part would be you give me the limit point of the support of an ordinary function, then you have to really play around to get this, but here we have used the Fourier transform. And the obvious thing is, if you're far away, then you're kind of in the middle of these areas of trivial action. And so whatever you do for approximation, you would never come close to the delta, and therefore, I leave out the other part. So I think it's a good moment to stop. Yeah, maybe just recalling that if you do this now on the Fourier transform side, instead of multiplying pointwise with k in S0 or just with S0 elements, that's even more general, then you are getting the same thing on the Fourier transform side. Weak star convergence goes to weak star convergence. So, and the delta goes to character chi s. So chi s is in this support if and only if you can filter it out, and the filtering means convolving it, the sigma, and you get this in the weak star limit. You have seen this is a fairly delicate point, but I will use it in different things. So I think we should accept it as a statement, and I take a break now and finish. Probably we'll do now a more practical thing in the second session and continue on Thursday with these things. Thank you very much for now.